Uh, we'll be continuing from the derivation of this half-wave rectifier. We in the earlier video we have discussed about the construction and operation of this half-wave rectifier, and right now we are going to calculate RMS value, efficiency of rectifier, ripple factor, etc. And what this equation represents, V is equals to Vm sine omega t, here is the applied voltage. V is equals to Vm sine omega t. So let us have this equation as equation number 1 here. And if you want to calculate this I, that is current, we know current is equals to voltage by, and we have the two resistances here. R is equals to small r plus RL here. So R is the forward bias resistance and RL is the load resistance, we know. And as compared to the RL, small r is very less, so that R it is almost 0. We'll say that this R is neglected here, so that I is equals to V by RL, we say. And in the place of V we can substitute the equation 1. This is Vm sine omega t by RL here, right? So this is the equation that represents during the appearance of this negative half cycles at S1, this diode is operated in the reverse bias, which offers infinite resistance, as we discussed in the operation of this half wave rectifier. That is, during the reverse bias, the current is almost nearly equals to 0 here, because it offers infinite resistance. So the output voltage during negative half cycle, what we can say, across the load resistance is almost 0 here. And what is the equation, that is we are obtaining the current, that is IDC. If we calculate the IDC, what we can say here, what we can involve here is, we can have the phase values here. Let us see. So during this process, which is repeating for half wave rectifier, that is the terminals of the S1 and S2 are altering for every half cycle, then we can say this IDC, that is output voltage, that we are obtaining here. We can have the equation 1 by 2 pi 0 to 2 pi here. We are taking the limits here, I into d, and this is of function d omega t here. And we can split this integration, that is IDC is equals to likewise 1 by 2 pi into, we can say 0 to pi here, and then I d omega t, and likewise here also integral from pi to 2 pi here, pi to 2 pi here, I into d omega t. So what we can say from this equation, the second term, this second term which represents 0, because as we discussed in the earlier equation, that during the negative half cycle, that is the almost it is having larger resistance, in it offers infinite resistance, so that I is almost nearly equals to 0. So this second equation, second term of this equation becomes 0, so that we'll get IDC is equals to finally 1 by 2 pi into this is 0 to pi I d omega t here, right? And if you calculate, that is, if you simplify this equation, that is, if you substitute in the place of I, as if you know from this equation I, so I value is, I is equals to here Vm sine omega t by RL here. So if we substitute this equation and simplify this equation, we will get the value for IDC here. Let us see that. So the value for IDC here, IDC is equals to here 1 by 2 pi into 0 to here pi. I, in place of I we are substituting this Vm by RL, this is sine omega t d omega t is this equation. And after simplifying this integration, we will be getting 1 by 2 pi, and this is Vm RL are constants, they are taken outside. And then after, if you integrate this, we'll get what, sin, for sine omega t we are getting cos omega t, negative cos omega t, so that 0 to pi here limits. And then if you simplify further, IDC is equals to, here we are getting Vm by pi RL here. So this is the equation that what we have obtained from this. And if you if you have the 1 by pi value, and this IDC is equals to, we all know pi is equals to 22/7, and if you substitute like this, likewise we will be getting 0.318 into here Vm by RL. So this is the equation that represents the output current, that is IDC, and from IDC we can calculate VDC also. How can we calculate VDC? VDC is equals to IDC into RL, because the load across the load resistance this current is taken out, right? Output voltage is taken out, so that VDC is equals to IDC into RL. And from that equation, what we can say, from this equation, if you calculate this IDC and VDC is equals to, you will be getting 0.318 into the maximum value of voltage Vm. So the final equation for this output voltage or VDC is equals to 0.318 into Vm. So using IDC equation and VDC equations, we have to determine number of factors like RMS value of current, efficiency of the half wave rectifier, ripple factor and form factors, etc. We'll check it out one by one. So this first one is what we are calculating here is RMS value of current here. So RMS value of current, what the equation here we are having, IRMS is equals to root of, according to definition, I average square here. So if you substitute that I average value, simply IDC value, and we'll be getting IRMS is equals to Vm by 2RL here. So this from IRMS we can also calculate VRMS. Okay, VRMS is equals to here Vm by 2 here. So likewise, if you substitute this equation, that is I average equation in the sense, what we can say, what we have calculated in the earlier one, that is IDC is equals to Vm by pi RL. Likewise, if you substitute that equation and simplify this square root, we'll getting Vm by 2RL, and from this IRMS, from the current value of RMS, we have the RMS voltage here, VRMS is equals to Vm by 2 here. And if you go for efficiency of the rectifier, what we can say, efficiency of the rectifier is, it is the ratio of DC power to the AC power. So here, if you know the efficiency of the rectifier, how it can be defined as, it is a ratio, that is it can be represented by using this eta, and that is by definition this is output power, that is PDC to PAC ratio. It is a ratio of DC power delivered to the load to the AC power inserted as input, so that the ratio is known as efficiency of the rectifier. So we know PDC equation, we know PDC is equals to IDC square RL. So this equation is the PDC equation. And if you go for PAC equation, so PAC is equals to here, PAC is equals to here Vm by 2RL whole square into RL here. And if you substitute these two, that is PDC square IDC square RL by Vm by 2RL whole square into RL, we'll be simplifying that eta, and then we'll be getting some equation. Let us see that equation also. So eta is the ratio of PDC to PAC. So this if you substitute like this, eta is equals to, we have Vm square by pi square RL by here what we can check, Vm square by 4RL here. So if you simplify this further, we'll be getting 4 by pi square. So how could we say Vm square and Vm square, and here RL and RN. If you reverse this ratio, we'll be getting 4 by pi square here. So therefore eta can be treated as 4 by pi square. If you substitute pi as 22/7, we'll be getting the equation and 0.406, or in terms of percentage we can say 40.6%. So efficiency of the rectifier means converting the rectification ability to rectify is only 40.6%. So the efficiency here actually shown by the half-wave rectifier is less than the half of a value, because the resistance offered by the diode can't be negligible under practical conditions. So we got the eta is equals to here 40.6%. And from this equation, these equations, we can calculate form factor and as well as ripple factor also. So we'll check it out, that one also. Form factor for a half-wave rectifier is simply, it is denoted as this is the ratio to IRMS to IDC. So this is a ratio of RMS value of current by average value of current, or else the IDC value. And if you substitute this Vm by 2RL, and this is Vm by pi RL here, and if you simplify further, we will be getting this is pi by 2, and also if we know this is 1.57. Form factor for half-wave rectifier here is 1.57, and likewise we can also calculate the ripple factor here. So ripple factor, how could we get ripple factor? We'll check this through some diagram. So ripple factor, which is defined as the ratio gamma is equals to, which is the ratio of IR to, that is ratio of current due to AC components present in the output to the average value of DC, that is direct current. I repeat, ratio of current IR due to AC components present in the output voltage to the value of IDC. So this gamma is equals to, we can represent it, we can say IRMS square minus IDC square by here IDC. So I'll be getting this as root of IRMS square by I square DC minus 1, if you further simplify this. And after simplifying this, we'll be getting 1.21 is the value for ripple factor for half-wave rectifier. That is, how can we conclude this? What we can say that gamma is equals to 1.21. What it shows? It shows the that AC components are present in the output which are more, and so the efficiency of conversion of AC voltage to the DC voltage is less than for a half-wave rectifier. As of we discussed, it has an efficiency of 40.6% only, and that means the remaining are the AC components that are present, which are calculated by using the ripple factor here. So that's what about the half-wave rectifier construction and operation, and then various factors, and that is what we have discussed: the RMS value of current, average value of current, and then form factor, ripple factor, and efficiency of the half-wave rectifier.